So I'm Tim at Julia Hub. I work on a variety of GPU backends, including CUDA.jl, Metal.jl, but today I'm going to give a brief overview of oneAPI.jl. So for those of you who aren't familiar with oneAPI is Intel's approach to cross-architecture accelerator programming. So in principle, they don't restrict themselves to only GPUs. oneAPI.jl, the goal of it is such that it can be used on a variety of accelerators, not only Intel accelerators. But right now, both oneAPI, the Intel project, and oneAPI.jl, our Julia package, focuses strictly on programming Intel GPUs. So it's one of the packages in a row to target one of the accelerator platforms that we have. Normally, oneAPI, it's an entire middleware, a framework. It comes with a C++-based programming interface. We, of course, replace that with Julia. It comes with a whole variety of libraries like oneMKL, oneDNN, and so on. And it also brings a whole slew of tools to profile, to debug code, and so on. So on the right-hand side, you can see that with Julia, we offer a similar programming experience that we have in the other GPU packages. You can do direct programming with kernels, with a kernel dialect that, again, looks intentionally very similar to all of the other backends, so that it's easy to switch from one GPU backend in Julia to another GPU backend. And of course, we also offer the API-based array programming that makes it possible to write generic code that should theoretically work across all of our GPU backends. So oneAPI.jl has actually been in development for quite a bit, and development is also just happening steadily. In this talk, I'm going to give an overview of what we've been up to for the past year. And summarize that involves including supporting more hardware, supporting more Julia versions, adding wrappers for oneMKL, integrating with vTune, and a powerful kernel abstractions backend as well. So briefly zooming in on each of these, the new version, the latest version of oneAPI.jl supports a whole new bunch of things. Most important of which, I guess, is the support for the discrete Intel Arc hardware, which is a new series of GPUs you can buy and put in your desktop. So not only the integrated ones that we had been using for the past couple of years of oneAPI.jl development. The nice thing about the whole oneAPI setup and this discrete hardware is that the only thing it requires is a sufficiently up-to-date Linux kernel. So we can actually build JLLs that not only provide libraries like we do in the CUDA stack, cuBLAS, and so on, but we can also ship the entire user space driver, which is essentially libcuda. In the CUDA system, you always still require to install an NVIDIA driver. With the oneAPI system, the only thing you require is the Linux kernel. So that's definitely an improvement compared to the other vendors here. We now support 1.6 to 1.9, and 1.10 is also being tested by CI and will come with a nice 20% latency reduction. This, of course, isn't specific to not specific to oneAPI.jl, but nonetheless, it's a nice feature to boast with. Platform-wise, we only support Linux. Windows could be theoretically supported, but as mentioned in a previous talk, that's not really of interest to this audience. And if you really need to use Windows, I've heard it's possible to use our Linux binaries through WSL2. One of the more interesting features we added this year is integration with oneMKL, which should drastically speed up many oneAPI applications that use BLAS level 1 to 3. So the tricky part here is that oneMKL, the Intel library, it only offers a C++ API. And of course, in Julia, we're not good with C++. So sadly, we had to write C wrappers that wrap the C++ APIs of oneMKL, and we did that in collaboration with Intel. So now we have a C API that's very similar to what you might be used to in cuBLAS or in the CPU BLAS. We use that to create Julia wrappers, and then we integrate those Julia wrappers with standard libraries like linearalgebra.jl. Again, very similar to all of the other backends we've got. This, of course, also means that it might be a little hard, or it might take some more effort to integrate with other libraries, because the first step is always creating a C wrapper for the C++ APIs. And only then we can start working on the Julia wrapper. So that's why library integrations have been taking a little while longer, but they're getting there. What's also important is, of course, integration with vTune, so that once you've written an application in Julia using oneAPI.jl, you can profile the application. vTune could already be used in combination with Julia to profile your own code. But we've done a bit of development to develop Intel ITT.jl, which is a Julia wrapper to interface with the Intel instrumentation and tracing libraries, which make it possible to enrich your timeline trace in a very similar way like we saw earlier today with mvtx.jl. So I stuck to the Intel ITT naming scheme here, but the add task is very similar to a range. Collect is the same as the add profile you have in CUDA.jl. So you have all of the same similar constructs. And as you can see on the timeline on the right, you can see my vadd range being annotated, and below that, all of the API calls that happen on the host. To generate this plot, you can use the vTune binary with -collect GPU offload, and you start the profiler in a past state, because with the add collect macro, we started on demand. And I've recently written a blog post documenting this all in detail, because with vTune, it's also trivial to do this on a remote system and then copy data back. Again, very similar to how Insight systems work. And similarly as to this works, how Insight systems work, if you want to look into how a kernel works specifically, you can use the GPU hotspot analysis, which compares to Insight compute, basically. It does give you less information, but nonetheless, it can be very useful to figure out why your memory copies might be slow, or how a kernel is stalling or not when it's being executed, scheduled on an Intel GPU. And the final large noteworthy contribution or improvement is a kernel abstractions backend, which makes it possible to not only write vendor-agnostic array codes, but also vendor-agnostic kernels, as you probably all know. So what's noteworthy here is the performance of these backends being compared on the right. This is a diffeq workload from a recent paper. So as you can see here, obviously, CUDA.jl performs the best, especially so at lower trajectory count, which means when the kernels don't take too long, because CUDA.jl basically has been nicely optimized over the years, meaning there's no type instabilities in host code, there's no inadvertent JIT compilation being triggered, and so on. On the higher trajectory counts, where the workload is much higher, all of the backends perform similarly. But it needs to be noted here that the Intel A770 I used here theoretically should be able to offer twice the flop count as the Quadro RTX 5000 I was using for the CUDA benchmark. So there is definitely still at least 2x performance gap being left on the table. But the question is, who leaves it on the table? If it's oneAPI.jl or maybe the oneAPI libraries, that's unclear at this point. We developed the vTune integration in order to be able to debug these issues and improve oneAPI.jl going forward. There's also been a slew of minor changes that don't require an entire slide to explain. We have multi-device support now, again, in a very similar way to CUDA.jl, where you can switch devices and query the current active device. We support shared buffers, which is basically unified memory you might be familiar with. And we also have a nice debug mode, where if you toggle this, we'll download different artifacts from Yggdrasil, which have debug mode and assertions enabled. And this is very convenient in order to see some more details about backtraces or to check some preconditions when running code. This is strictly for using oneAPI.jl on hardware that may be unsupported, or where you may suspect there may be a bug in the backend driver. So going forward, as I've shown with the kernel abstraction slide, kernel code already performs reasonably well, but the array abstractions need to be optimized, because many of these were developed for CUDA.jl, and even though we've ported them to the other backends, that doesn't mean that, for example, the launch configuration or the hardware features that we use are optimal for this platform. So specifically, for example, the MapReduce kernel is pretty slow and should be optimized for oneAPI Intel GPU backends. We also should be supporting more vendor libraries, but as I mentioned, the need for C++ API wrappers made this a little slow. And finally, of course, application support is something that needs to be improved or at least validated. So definitely here, try it out. If you have a kernel abstraction-based or an array abstraction-based application, try oneAPI.jl out. The benefit is that many people probably will have an Intel GPU. Well, maybe not the MacBook audience, but at least if you have an Intel CPU in your processor, chances are you might just be able to run oneAPI.jl just like that. And that's it for a short overview of the past year of developments. If there's any questions, now is the time.
Have you tried using oneAPI with like Aurora? I think it's Aurora, the big Intel supercomputer that has the Xe GPUs.
Yeah, that's the reason we developed it, but I don't have access to it yet. I heard it's delayed again, so I'm not sure. People here will probably know better what the status of that is.
Are there any plans to support CPUs with oneAPI?
Yes, as soon as oneAPI itself decently supports many more backends, we will definitely consider opening up oneAPI.jl and trying to make it more than just an Intel GPU package, but more of a broadly supported accelerator programming platform. The problem there is that, as I understand it, Intel itself doesn't exactly know yet how to move forward best on this regard. And for example, there's no proposals to introduce a new runtime library that would require us to re-engineer a significant part of oneAPI.jl. So I'm holding the boat off a little bit to see how things change in the next year. But we'll definitely consider supporting more platforms and different platforms as we go.
Can you hear me? So I have a question about like how kernel abstractions and GPU arrays.jl interfaces with oneAPI, because right now, like with CUDA.jl has like the best support for like all the library stuff, like cuSparse, CUA50, everything is ported, is actually getting regularly maintained, whereas in the AMD GPU.jl is lagging a little bit behind. Right now, like no rocksparse support, like you have Rocket50 support. But like from looking at the code, I understand like there's a lot of overlap between the code bases, like for like sparse and stuff. Like I was wondering, like if like with addition of like oneAPI and Metal, is there going to be like any effort to kind of abstract a lot of that away in like kernel abstractions and GPU arrays and like make the development a little bit more simpler across GPU stacks? Or
good question. The problem is that currently the scope of GPU arrays, at least, is to support whatever we can do natively. So as soon as we have to go to vendor libraries like cuSparse or Rocksparse or whatever the Intel equivalent is, it's fairly hard to figure out the exact level of abstractions, what we can put into GPU arrays and what we should abstract away. So there used to be a time that GPU arrays assumed that you had a GPU BLAS library and it had a bunch of functionality calling out to BLAS, and then you had to slot in a vendor BLAS library. The problem is that cuBLAS is not BLAS. It has its own APIs that slightly differ from, and the effort required to go and figure out within GPU arrays what the necessary changes are to the abstractions to support all of these slight varieties across vendors is hard for the development team that we currently have. So that's why all of the vendor-specific stuff is handled in the libraries itself. So cuSparse lives in CUDA.jl. Rocksparse will always live in AMD GPU.jl. And GPU arrays is only the stuff that we can do natively. Of course, at some point, and we started some efforts for that in CUDA.jl, we'll start having native sparse array support. We, for example, now have a native cuSparse device array support with broadcast implemented on top of it. If that functionality grows, that we can always move to GPU arrays because we can compile that for all of the other platforms. But API calls to a specific BLAS-like library, difficult to generalize.